Okay, in this video, I'm going to try and wrap all this up. Uh, Here we have, in my case, 15 equations for the 15 10-second subs I did. This is 20 seconds, 40 seconds, 60, 80, on down to a total of 300 seconds. And these are the equations relating magnitude to signal-to-noise ratio. So what we need to do is take these equations and create another table. Come to Excel, create a new Excel spreadsheet. And what I'm going to do is just go down here, 1, 2, 3, in Excel and in LibreOffice. You can highlight a series and then drag down here and go to 10. You can usually just type in 1 to 10. These are going to be our signal to noise ratios, so I'll put SNR here. Across the top, we want exposure times, and I did them in increments of 20 seconds. So here's 20, 40, and if I highlight these two and then continue across over to 300. So these are going to be exposure times. 20, 40, 60, up to 300. Okay, now go back to these equations. What we're going to do, remember this is the equation, the top one here is relating signal to noise ratio and magnitude for a total exposure time of 20 seconds. So we want to put this equation going down this column here, and the variable x is going to be the signal to noise ratio. So let me just show you how I do that. Right click on the highlighted part, copy, come to this first cell and go equals and then control V. Okay, now we need to clean this up a little bit. Need to put an asterisk in here because it's multiplying, and it isn't ln of x, it's ln of this cell value here. So I see what we've done here. We've inserted an asterisk to indicate a multiplication, and we replaced x with this value here. Hit enter. And again, in Excel and probably LibreOffice, you can come over here to this corner, you get the solid cross, and just drag it on down. So what this is showing you is that for my 20-second stacked image of two 10-second images, stars of about 17.9 magnitude are going to have a signal to noise ratio of 5. Stars of about 17.2 magnitudes are going to have a signal to noise ratio of 10. Okay, come to the next column. This equation here, Control C equals Control V. Come up here, put an asterisk, replace the ln of x with this, and then carry it on down. We'll do another one. 60 seconds is this one. Control C equals Control V. Put in an asterisk. Replace the x with a 2. Carry that on down. We'll do one more. 80 second. Highlight this. Control C equals Control V times A2, and bring it on down. Okay, and you just go all the way across here for each one of these equations. When you're done, you will have a nice table that looks like this. Okay, so here is all of our data, the new table filled out, and I've highlighted the two header columns here in the column and the row. Now you can also kind of make this look a little better if you highlight there. Instead of having it general, go to number. You know, really we're not concerned about hundredth of a magnitude, so you can even drop this down, oops, you know, to a tenth of a magnitude. That's plenty accurate. I'll leave it like that for now. But really, you know, a tenth of a magnitude here is actually more accurate than need be. And we'll talk about that in just a second. So now we're ready to do our first graph of how faint can you go with a given signal to noise ratio. So what you want to do, let's insert a blank scatter chart here. Right click, select data. We're going to add a series. We'll call this SNR equals 5. Okay, now the values, the X values are going to be the times, and the Y values are going to be, here's a signal to noise ratio of 5, so we're just going to go across here and grab these magnitudes. Okay, see what I've done here? So here is a plot of exposure time on the bottom in seconds versus magnitude, and this is for a signal to noise ratio of 5. You can come in here and fit a trend line through there. Logarithmic, let's show the equation. Okay, got a correlation of 0.9929. That tells me that this process is pretty valid. In fact, we're using, you know, 1, 2, 3, 4, 5, 15 equations going down here to create a series of magnitudes, and then we're using the data going across here. So this line is based on 15 different equations. They all line up very nicely. So here is a plot for a signal to noise ratio equals 5. We can right click on that, select data. Let's add another series called SNR equals 10. Again, the X values are going to be time, and this time the Y values are going to be down here along the signal to noise ratio of 10. And you know, we can fit a trend line through there. Logarithmic, and we can display the equation. Just here the correlation is 0.9904. That's very good. And you can see the difference between the plot of SNR equals 5 and 10. Let me make this a little bigger. And this all makes sense. You know, for a signal to noise ratio of 10, the stars you know, are going to have to be brighter for a given exposure time. So here's, you know, 50 seconds. stars of about 17.6 or 7 are going to be at a signal to noise ratio of 10. But if you want to get down to a signal noise ratio of 5, then that'll get you down to maybe 18.6 or 7. You can come in here and add some grid lines. To better refine picking numbers out of here. So you can create graphs for signal to noise ratio of 5, 7, 10. It's up to you. 10 is kind of where if you are able to do photometry with reasonable accuracy. 5 is about where you can be pretty sure of what you're seeing is really there. A signal to noise ratio of 4, 3, or 2, it's getting lost in the noise or very close to it. Can't be too sure of a measurement in there. So what I'd like to do is actually move this chart to a new page, talk a little bit about extending these out. If you come here to layout, and you can either click on the trend line or you can select it here. Let's do the signal to noise ratio equals 5. And click on format selection and this forecast. If you extend that out, forward, I don't know, maybe let's try 10 and see what we get. Okay, it didn't extend out very much at all. Let's try extending it out 50. Let's try extending it out maybe 100. So what we're doing is we're actually extending this graph out 100 seconds beyond the end of our data. And if you want, you can go out maybe quite far. And this will give you an idea of if you want to continue to go fainter than your data was taken, it's you can extend that trend line out. You've got a very good correlation here, so you can trust this graph out here. So this is telling me that if I want to get down to 20th magnitude, I've got to take a total of 600 seconds if I want to get a signal to noise ratio of 5. If I want to try doing that for a signal to noise ratio of 10, I select that trend line. And if I push that out 500 more seconds, I am not anywhere near 20th magnitude. In fact, if you look at this, I'm going to have to push this out to a very, very long exposure. Actually, a ridiculously long exposure. So I'm not going to be able to get 20th magnitude objects with a signal to noise ratio of 10. It's just not going to happen with my equipment from my location. So that's how you can plot exposure time versus magnitude and pick a signal to noise ratio. Now, if you do this, if you have other series, like a 30-second series, a 60-second series, a 5-second series, you can grab all of the equations for, say, signal to noise ratio of 5, and you can plot all of those on one graph. So here's a plot of my data. This is summarizing all of the signal to noise ratio of 5 plots. And here you can see the blue line represents my 2-second subs. The red is my 5-second subs, 10, 20, 30, 60. Those are all these plots here. And you can see they're all pretty good in agreement, except for this 2-second one, which is down below. It's not, what this is showing is that this 2-second sub series is just not doing a good job of adding up, integrating stars and stacked images. And I'm attributing that to the read noise that is present. You know, for this 300-second exposure, that's 150 2-second subs. So there's 150 read noises in there. So I'm guessing that's what's causing this different shape to this 2-second plot. Now, something we need to talk about is error. There's a rule that relates signal to noise ratio to the error of magnitude. And the error in magnitude is about equal to, I believe, 1.086 over the signal to noise ratio. So what that means is that for a signal to noise ratio of 5, which is pretty noisy, the actual error in the magnitude is a 0.22 magnitudes. So in reality, you know, when I come across here and I say I'm going to take an image of a 19th magnitude object and I want to get a signal to noise ratio of 5, and I come over here in the graph and I see that I need to be somewhere around, you know, what, 110, 20, 130 seconds maybe. Well, these error bars carry this up and down quite a bit. So what I typically do is, you know, if I'm trying to image something at 19th magnitude, I go up at least 2 or 3 tenths more. Come over here and say, okay, this is probably where I want to be sure I get this object. I really need more, like 200, 220, maybe 250 total seconds to be sure that I get this thing with at least a signal to noise ratio of 5. So it's important to keep in mind, you know, the error that's associated. If you want to go up to a signal to noise ratio of 10, these are all the plots for signal to noise ratio of 10. You can see it drop down considerably. It's the same scale as this one. And the error is much less. It's about 1/10 of a magnitude here, plus or minus. So that's one, you know, unit on this graph. Also, this 2-second plot is really starting to diverge from the rest of these. Here, the 5-second plot is the kind of the next least efficient imaging. But sometimes I have to go this fast when I'm doing astrometry of near-Earth asteroids, and they're moving so quickly. In order to capture an image without any trailing of the asteroid, I sometimes have to take 2-second subs or 5-second subs. So that hopefully ties everything together on how you get from a series of stacked images of a blank star field to a graph showing a relationship between signal to noise ratio and magnitude, and then taking that data and transforming it into a graph and a plot of magnitude versus exposure time for a given signal to noise ratio. And hopefully this will be of use when you're actually taking images to give you a better idea of what exposure time you need in order to record something. So I thank you very much for watching.